Now, as of this morning, some observers noticed that it has a sequence, a set of jets around it, more than 7. Some headed towards the sun, some away from the sun. It's a spectacular view that we have right now after it passed closest to the sun on October 29th. It became bluer than the sun. It was 5 times brighter than it was before it came close to the sun.
Wow.
So the action is happening right now, and in the coming days and weeks, we should learn much more about it.
Astronomers are now watching more than 7 jets firing from the interstellar object 3I Atlas. Simultaneously, some of these jets are aimed toward the sun, others are directed away from it, as if the object is actively adjusting its motion in real time. And the movement is measurable. 3I Atlas has changed its trajectory, receiving a velocity boost equivalent to a jet pushing 5 billion tons of material. Yet there is no cometary tail, no dust cloud, and no visible mass release that would normally produce such a powerful recoil. Right after swinging past the sun on October 29th, the object suddenly became 5 times brighter, and its color shifted to become bluer than the sun itself. Under normal heating, it should have turned redder. It didn't. That color change does not match standard comet physics, and no clear explanation has been confirmed. Dr. Avi Loeb states that the major focus now is determining what is powering these jets and whether 3I Atlas may have released smaller objects as it passed the sun. Observatories will be watching near Earth and near Mars in the coming weeks. The behavior of 3I Atlas has already required astronomers to pause and reevaluate what is expected when an interstellar object moves through our solar system. Unlike comets that originate here, which are shaped by billions of years of exposure to the sun, the Kuiper belt, and the Oort cloud, this object approached from deep interstellar space, carrying a thermal, structural, and compositional history we have not encountered directly before. But even allowing for unfamiliar chemistry or geological evolution, the observed behavior does not map neatly onto any known pattern of solar system comet dynamics. One of the first points Dr. Loeb emphasizes is that the observed acceleration, the deviation from predicted gravitational orbit, cannot simply be left unaddressed. Orbital mechanics is one of the most precise and well-tested areas of astrophysics. When an object does not follow the path dictated by the gravitational fields acting on it, something has changed the forces acting on its motion. In comets, this force often comes from the venting of sublimating ice. Such jets typically release visible gas and dust, which expands outward under solar heating and radiation pressure. The absence of a tail in the case of 3I Atlas means that if sublimation is occurring, it is not behaving the way it does in every well-studied comet to date. In a recent analysis, images taken after perihelion revealed that the jets around 3I Atlas form an extended structure that can reach hundreds of thousands of kilometers in scale. The shape of this structure is not uniform, but instead appears to taper in regions and expand in others. The jets form a kind of envelope around the object, creating a luminous region large enough to compare to planetary-scale distances. This envelope is not chaotic. The jets retain directionality and shape across their extent instead of dissolving into a diffuse cloud. That level of coherence is rare among known natural jetting processes. The alignment of the jets is another key point. Jets pointing toward the sun are difficult to account for using standard sublimation models, because solar heating normally causes volatiles to sublimate on the sun-facing side. In that case, gas generally expands away from the sun, carried outward by solar wind. For some jets to point toward the sun suggests that the venting is not solely controlled by surface temperature gradients. Either the object has complex internal pathways that channel material along specific fault lines or fractures, or the jets are being produced by pressures and orientations that do not depend solely on the heating direction. Both interpretations require new modeling. Then there is the issue of brightness and color. The increase in brightness by a factor of 5 suggests a dramatic change in the object's reflective or emissive properties. Brightness could increase if the object released reflective particles, such as ice crystals or fine silicate dust. But if that were the case, those particles should scatter sunlight preferentially in longer wavelengths, causing reddening. The shift toward a bluing reflectance is inconsistent with standard dust production. A bluing effect requires scattering of shorter wavelengths, which typically occurs with particles much smaller than those released by standard cometary surface venting. This leads to the question, what exactly is causing the bluing? He notes that 3I Atlas did heat up as it approached the Sun, but its surface temperature remains far below the Sun's temperature of about 5,800 degrees Celsius. Under such conditions, most comet-like bodies become darker and redder, not brighter and bluer. Dust particles released from comets tend to scatter longer wavelengths of light, the reds and yellows, especially as their surfaces heat and break down into coarser grains. For 3I Atlas to reflect more blue than the Sun means that the material surrounding it is interacting with sunlight in a way that selectively enhances shorter wavelengths. That is not the behavior of typical dust, ice grains, or carbon-rich materials seen in known comets. One possibility is fine particle scattering at extremely small scales. If the object is releasing particles orders of magnitude smaller than typical comet dust, particles closer to nanometer dimensions, they would preferentially scatter blue light through a process similar to Rayleigh scattering, the same effect that gives Earth's sky its blue color. But producing such fine, uniform particles requires physical conditions that differ greatly from the fragmented dust plumes of standard sublimation. This would imply a breakup or release mechanism capable of grinding or vaporizing material into extremely small, controlled-sized grains, which is not observed in ordinary cometary outgassing. Another possibility raised in spectroscopic discussion is that molecular emission may be contributing. Certain molecules, when exposed to solar ultraviolet radiation, can emit light at specific short wavelengths, producing a bluish glow. However, for this to dominate the object's visual profile, the molecules would need to be present at consistent densities, not expanding rapidly into space. Standard comet behavior, in contrast, produces expanding gas envelopes that dilute quickly under solar wind pressure. The observations of 3I Atlas show no such broad envelope, meaning if molecular emission is occurring, it is either confined or sustained in a way that is not yet understood. A third consideration is surface reflectivity. If fresh material, possibly ices, silicates, or other reflective crystalline structures, was exposed during perihelion, it could temporarily enhance reflectance of shorter wavelengths. But this would also usually be accompanied by more noticeable surface fragmentation or visible dust shedding, neither of which has yet been identified around the object. The brightness increase came without the expected debris signature. It brightened, but it did not shed. It scattered more blue light without releasing detectable amounts of reflective dust into space. Whichever of these mechanisms, or combination of them, is responsible, none of them aligns with standard comet behavior near the Sun. The bluing is not simply unexpected, it is a diagnostic deviation that signals physical conditions or compositional properties that current comet models do not account for. It is one of the clearest indicators that 3I Atlas is behaving in a manner that does not match the known behavior of solar system objects undergoing heating and outgassing near perihelion. Supporting this, radio observations reported in one of Loeb's follow-up analyses detected absorption signals from hydroxyl OH molecules at 1.665 and 1.667 GHz. These molecules typically form when water vapor is broken apart by solar ultraviolet radiation. Their presence means that water-bearing material is present near the object. However, the hydroxyl signature did not appear in a broad expanding halo. Instead, the molecular absorption appears localized. Water vapor is present, but it is not dispersing in the classic fashion of a comet outgassing into the solar wind. This confinement of hydroxyl radicals suggests either low-velocity release or some form of structural or environmental constraint on gas motion. The extent of this confinement is now a central focus of radio telescope monitoring efforts. The question of whether 3I Atlas has released smaller bodies is particularly significant for ongoing monitoring. If compact fragments or secondary objects separated from it during perihelion, they would now be traveling along their own trajectories. Depending on their velocity and direction, some could eventually pass through regions where planetary orbits intersect, meaning that their paths need to be charted carefully. Although no fragments have been confirmed, the situation calls for active surveillance. Research teams will review wide-field sky survey data for faint objects whose motion matches the expected velocity profile of secondary releases. NASA instruments can also monitor the region near Mars, where any recently separated bodies would currently be most likely to appear. This stage of observation resembles a methodical investigation. The object has already passed its closest approach to the Sun, and the challenge now is to interpret its behavior as it travels outward, where the glare of solar illumination is reduced and finer detail can be resolved. Over the coming days and weeks, telescopes on Earth and in space will collect higher-resolution imagery and spectral data. The bluing effect may diminish as the object cools, or it may intensify, or shift into a different spectral profile entirely. Likewise, the configuration of the jets may change if their orientation is linked to the object's rotation. If the jets remain aligned in consistent directions, even as solar heating conditions decline, that would be a significant observational result. The structured halo around 3I Atlas observed after perihelion appears to follow consistent shapes over significant distances. The outer layers of the halo are faint, yet they retain defined curvature. The extended branching and smooth tapering of the jets are distinct from the filamentary, unstable plume structures seen in comets shedding heterogeneous mixtures of dust and gas. These smooth features suggest that whatever material is forming the halo is distributed through a consistent channeling mechanism. At the same time, the brightness and color change means that the surface or near-surface optical properties of the object have changed. This could indicate that new surface layers were exposed during perihelion, that finer particulates were released, or that a layer of volatile material transitioned into a different state. However, without knowing the original surface composition, the degree of thermal penetration, or the internal porosity of the object, the exact cause remains undetermined. The central issue is that each standard explanation solves only part of the problem. Sublimation explains hydroxyl radicals, but not the lack of a tail. Thermal venting explains jets, but not the bluing. Dust release explains brightening, but not directional confinement. And none of these processes, individually or combined, fully accounts for the recoil acceleration without visible mass loss. Caution is warranted at this stage. No estimates about potential origins are being updated because additional data is required before any conclusion can be justified. The priority now is continued observation as the object moves into a region of the sky where more telescopes can track it continuously. Hundreds of ground-based and space-based observatories are positioned to gather measurements across multiple wavelengths. Spectral data will refine the understanding of the recent color shift. Sequential imaging over time will show how the jets evolve as the object rotates and moves outward. Radio monitoring will track whether hydroxyl signals strengthen or fade. Infrared measurements will provide information about how the surface temperature changes as solar heating decreases. The next phase depends on patient, systematic data collection rather than early interpretation. The next phase is not speculation. It is accumulation, refinement, and comparison of data. The situation is still unfolding. The jets are active, the motion has changed, the color shift remains unexplained, and astronomers are watching closely, not only to understand what 3I Atlas is doing now, but to learn how to interpret the behavior of any future interstellar objects that may enter the solar system. Another such object is already being tracked, though data on it is not yet developed enough to draw conclusions. It will take time, but the process of developing an understanding begins here, with close attention, careful measurement, and the willingness to let the evidence lead rather than assumption. The investigation continues, the observations continue, and whatever 3I Atlas is, or whatever it is doing, will become clearer as the weeks go on, as more telescopes turn toward it, and as the sky slowly reveals the next chapter.